Linear algebra is a branch of mathematics that is concerned with mathematical structures closed under the operations of addition and scalar multiplication. And that includes the theory of systems of linear equations, matrices, determinants, vector spaces, and linear transformations. In simpler terms, linear algebra is the backbone of modern mathematics and science. It's a universal language that is foundational to countless fields from physics and engineering to computer graphics, data science, and machine learning. By mastering linear algebra, we develop tools to represent, analyze, and solve problems across virtually every discipline. The most basic notion in linear algebra is the set. A set is a collection of elements. Note that I say elements and not numbers, because a set could consist of the numbers between 0 and 20, or it could consist of the days in the week. We could even have a set that's empty, which we denote by a 0 with a slash through it. These collections are unordered and do not respect repetition. I like to think of sets as collections for things that I can use. If I want to prove that any element in this set, negative 2, 2, 2, negative 2, 2 equals 4 when it's squared, all I need to do is prove that negative 2 and positive 2 squared is 4. I don't care whether I'm working with the first 2 or the second 2. All I care about are the unique elements in the set. So the set may as well be rewritten as negative 2, 2. Another important quality of sets is that they need to be well defined. If I say the set of numbers greater than 5, it's clear which elements are in the set and which are not. We say that a subset is a set where every element in that set is also in another set. If A is 1, 2, 3, and B is 1, 2, 3, 4, every element of A is also in B. So A is a subset of B. We can say that a set is a subset of itself, since all of its elements are in itself. And trivially, the empty set is a subset of all other sets. Looking at two sets, if every element of A is in B, and every element of B is in A, then A and B contain exactly the same elements, and therefore are equal. Just like how we can define operations on numbers, we can define operations on sets. These operations include the union of sets, the intersection of sets, the difference between sets, and the Cartesian product of sets. These operations create a new set from the sets that they act on. We can express these set operations visually. Let's imagine two sets that overlap to form a Venn diagram. The union of the sets includes all the elements of both sets, so it would be the entirety of our Venn diagram. The identifier is a U-shape, and I like to think of it as a container. When you have a container that is upright, it allows for everything to go into it. The intersection of two sets is only the elements that are contained in both sets, so it would be the intersection of our Venn diagram. The identifier is an upside down U-shape, and I also like to think of it as a container, but because it's upside down, it's closed off. The difference between two sets is a set of elements in one set that are not in the other set. We can think of it like removing the elements of the second set from the first to show off the unique elements of the first set. The difference of A minus B is all of A without any of B, and the difference of B minus A is all of B without any of A. A special case of the difference is the symmetric difference. This is the set of elements that are in either A or B, but not both. It's the union of the difference of A to B and the difference of B to A. On our Venn diagram, it's everything except the overlapping region, kind of like the opposite of the intersection of sets. Thinking about opposites, we can briefly look over the complement of a set. The complement of a set isn't a set operation, but like how a set operation generates a new set from the set that it acts on, the complement of a set generates a set which is all the elements that are not in the original set. If A is the set of odd numbers, then A complement would be the set of even numbers, or all numbers which are not odd. So we can think of the complement as the opposite of a set. Finally, the Cartesian product of two sets is best visualized as a grid, where the rows represent elements that are in the set A, and the columns represent elements that are in the set B. Each cell represents an ordered pair based on its position. So the first element is from the set A, and the second element comes from the set B. It's important to note that A cross B is not the same as B cross A. We can see that the pairs change order if we switch the rows and columns. What was once the pair A1-B1 is now the pair B1-A1. These pairs are different. Just like how a point on the graph 1, 3 is not the same as the point 3, 1, the order matters in our ordered pairs. We can express these set operations in writing. If we have the sets A and B, where A is 1, 2, 3, and B is 3, 4, the union of the sets is all the elements of both sets combined. So the union of A and B is 1, 2, 3, 4. The intersection of sets is only the elements that are in both sets, so the intersection of A and B is just 3. The difference of sets is the elements of the first set without any of the elements of the second set, so the difference of A and B is 1, 2, while the difference of B and A is just 4. The symmetric difference is the elements in A or B, but not both. So the symmetric difference of A and B is 1, 2, 4. The Cartesian product of the two sets is a set of all the ordered pairs where the first element comes from the set A and the second element comes from the set B. So to form the Cartesian product in writing, we take the element from the first set, pair it with all the elements of the second set, and then repeat for the rest of the elements in the first set. So we could take the first element in A, 1, and make the pairs 1, 3, and 1, 4. Then we take the second element in A and make the pairs 2, 3, and 2, 4. And finally, we make the pairs 3, 3, and 3, 4. Going back to sets themselves, there are some foundational sets. The set of natural numbers is a set of non-negative whole numbers. The integers are any whole number, positive or negative. Rational numbers are numbers that can be formed as a fraction of whole numbers, whereas irrational numbers are numbers that cannot be formed as a fraction of whole numbers. The real numbers are all the numbers listed so far, and complex numbers include imaginary numbers, like the square root of -1. If we look at the set of natural numbers, it's a subset of the integers, which is a subset of the rational numbers, though the irrational numbers are separate. Combining them, we can form the real numbers, which is a subset of the complex numbers. Putting it all together, we can form a very nice diagram to see how the sets that define our number system are interrelated. Note, the natural numbers can be described as the set of positive integers or non-negative integers. These two sets are different, since 0 is neither positive or negative, so it is not included in the set of positive integers, but it is included in the set of non-negative integers. Be aware of which definition you're using, and make sure that you're consistent with it.